So in this video we are going to solve question on our topic analysis of pre-stress. So this is our question. It says a rectangular concrete beam 100 mm wide by 250 mm deep, okay, spanning 8 meter, is pre-stressed by a straight cable carrying an effective pre-stressing force of 250 kilonewton located at an eccentricity of 40 mm. The beam supports a live load. Of 1.2 kilonewton per meter. This question has two parts, and we are going to solve both the part. Calculate the resultant stress distribution for the center of span cross section assuming density of concrete as 24 kilonewton per meter cube. We know the density of concrete is 24 kilonewton per meter cube, and this data is also given here. Okay, so going to solve this question. So the question is, once again I am going to repeat, a rectangular concrete beam which is 100 mm wide and 250 mm deep, and the span of the beam is 8 meter, and is pre-stressed by a straight cable carrying an effective pre-stressing force of 250 kilonewton located at an eccentricity of 40 millimeter. The beam supports a live load of 1.2 kilonewton per meter. Okay? So we have to calculate the resultant stress distribution for the center of span cross section, because the center of the span has a maximum bending moment, WL square by 8. So we are going to calculate that moment, and that bending moment for both live load and dead load also. So we are going to solve this question. Okay, so first you have to calculate this, how to approach this solution. Okay, So the resultant stress distribution. So there will be pre-stress because there are pre-stressing forces. Pre-stress, direct compressive pre-stress due to pre-stressing force, that is equal to P by A. Okay. Also there will be bending pre-stress. Bending pre-stress, that will be P by ZT at the top, P by ZB at the bottom. Also bending stress, due to dead load is equal to M by Z T at top and Q by ZT is equal to MQ by ZB at bottom. Bending stress due to live load is equal to mg by zt at top, mg by zb at bottom. Okay, so P is given is 250 kilonewton. P is 50 kilonewton. A is B into D. Our B is 100 mm and D is 250 mm. So the cross sectional area will be 100 into 250, 100 mm into 250 mm. This will be 250 into 10 to the power 3, 10 to the power 2, 10 to the power 2 millimeter square. Now, what other things we have to calculate? Other things are, we know P, we know eccentricity 40 mm, E is 40 mm. We have to calculate ZT and ZB. These are important. Also MQ and MG. Okay. So ZT is equal to I by Y T. Okay. So I we know from CG of the rectangular section, I is BD cube by 12, we know that, and if this is NA, then YT is equal to D by 2. So D by 2, this will be equal to BT square by 6. Same ZB is equal to I by YB. You know, same I, second moment of area is equal to BD cube by 12. Then YB is also same, D by 2 from neutral axis to the bottom distance, bottom fiber distance. This is, if this hole is D, then half here D by 2 and half to the top D by 2. So this will be BT square by 6. So both value will be same. Zt is equal to Zb, it will be Bd square by 6. B is 100, D is 250 का square divided by 6. So if we are going to use calculator, then this value will be we're going to use calculator. This value will be 1041.67. Okay, so I've done some mistake. Sorry, 1041.66. Okay, so this will be, this value will be 10 or 1.04 into 1 2 3 4 5 6 into 10 to the power 6 millimeter cube dimension. Okay, this is our Zt and Zb. Now we have to obtain mg, mq and mg. Okay, so for that we have to calculate q and g. Q is equal to dead load intensity, it will be equal to density of concrete 24 kilonewton per meter cube. So per meter cube 1000 mm, 24 kilonewton, kilo 10 to the power 3 newton, and per meter cube, so we change 1 meter to 1000 mm power cube into section cross sectional area is 100 and 250. Calculator 24 into into 100 into divided by divided by 10 to the power 9, because cube, so it will multiply on 10 to the power 9 is equal to 0.6 Newton per millimeter. Okay, 0.6 Newton per millimeter, and our live load intensity is given in the question. It is 1.2 kilonewton per meter. Simply write 1.2 kilonewton per meter. We're going to change 10 to the power 3, changing kilonewton into newton and meter to 1000 mm. So it will be 1.2 Newton per mm. So this is LL and this is G. So we add simply Q plus G, it will be 0.6 plus 1.2 is equal to 1.8 Newton per millimeter. Okay. So the combined moment mq plus mg will be, this will become our W. So 1.8 into L square. L is 8 meter. L is 8 meter. So we are changing this meter. Okay. So we are going to change this meter. So it will be 8 into 10 to the power 3, 8000 millimeter. So W L square divided by 8. So using calculator we simply write 1.8 into 8 into 10 to the power 3 whole power 2 divided by 8. So this is our result, 1.44 into 10 to the power 7. Okay, Newton millimeter. This is mq plus mg. So for bending stress, bending pre-stress first. Bending pre-stress, it will be E by Z, because both ZT and ZB are same, so we are not going to calculate separately. Same. Okay. So P is our pre-stressing force. Pre-stressing force is 250 kilonewton. 250 into 10 to the power 3. Eccentricity is 40 mm. Z we have calculated 1.04 into 10 to the power 6. 1.04 into 10 to the power 6. So once again we are going to use calculator to obtain this value. So 250 into 10 to the power 10 to the power 3 into 40 divided by 1.04 into 10 to the power 6. So this value will be, obtain this value, 9.6 Newton per mm square. This is bending pre-stress. Now bending stress. It is m by z. So our m is 1.44 into 10 to the power 7. 1.44 into 10 to the power 7 Newton mm, and z is section modulus 1.04 into 10 to the power 6. So 1.44 into 10 to the power 7, 1.04 into 10 to the power 6. Value is 13.85. Value is our 13.8. Simply write 13.85. Same unit, stress unit is Newton per mm square. So obtained all the results. Direct direct pre-stress. Direct pre-stress is, oh, we have not obtained that, so we also obtained the direct pre-stress. Okay, so direct pre-stress is equal to P by A. P is 250 kilonewton. Okay, so 250 into 10 to the power 3 Newton. Area is 100 into 250. So this value is simply 10 Newton per mm square. Okay, so now we are going to finally find the resultant stresses. Resultant stresses at the top of beam. So it is first direct pre-stress 10 Newton per mm square compressive minus P by ZT. So P by ZT we have obtained P by Z or P by ZT same 9.6, but value is minus, so minus 9.6 plus bending stress M by Z, and this value is 13.85 plus 13.85 Newton per mm square. Okay, per square. Second, at the bottom of beam is equal to, once again same 10 uniform pre-stress direct stress plus P by Z. So P by Z B, so P by Z, Z and Z be same, so P by Z it is 9.6, so this sign will be plus 9.6, then minus bending stress M by Z. So M by Z is 13.85 minus 13.85 Newton per mm square. So this value is 10 minus 9, 10 minus 9.6 plus 13.85. This is 14.25 Newton per mm square. Okay, and for bottom is 10 plus 9.6 minus 13.85. This value is 5.75 Newton per mm square. So our results are obtained. Both are compression, because positive, no negative sign. Negative sign indicates tension, but positive sign indicates compression. So both are. So we obtained this first, done this first part. Now second part. Second part of question is find the magnitude of the pre-stressing force with an eccentricity of of 40 mm, which can balance the stresses due to the dead and live loads at the soffit of the center span section. Okay, so the second part of the question is very different from the first part, because here we have to calculate the pre-stressing force such which is at a centricity of 40 mm and which can balance the stresses due to the dead and live loads at the soffit of the center span section. So we have to calculate the pre-stressing force. Okay, so P is our P is given 40 mm. So at the soffit means at the bottom, at the bottom resultant stresses is equal to E by A plus E by Z minus M by Z, Z or ZB, whatever you write. Okay, so here the question is, find the magnitude of the pre-stressing force with the eccentricity of 40 mm which can balance the stresses due to the dead and live loads at the soffit of the center span section. So here our question is such that the stresses due to the dead and live loads have to balance. Okay, so you have to balance such that it means that these pre-stresses will balance the stresses due to dead load and live load. So magnitude of the pre-stressing force which can balance the stresses due to dead and live loads. This is stresses due to dead load and the live load, and this will pre-stressing force, and the resultant pre-stress P by A plus bending pre-stress. So this balance this, it means that P by A plus P by ZB will be equal to M by ZB, then they are going to balance. Okay, so we simply write this. Now we have nothing to do, we have done the calculation part. P by A we have obtained, this is 10 plus P by ZB, P by ZB we have also obtained, this is 9.6, same 9.6. oh sorry, this is wrong because the value of pre-stress is different. So P by A, area is 250 into 100 plus PE, P into 40 by ZB. Z is simply 1.04 into 10 to the power 6. Now M is M by Z, we directly write M by Z. Okay, that is 13.85. we have to obtain now P. So we take P common. If we take P common, here P is taken common, then in the bracket 1 by 250 into 100, 40 by 1.04 into 10 to the power 6. So 1 by 100 into 250 plus 40 divided by 1.04 into 6, 10 to the power 6 is equal to 13.85. This will give our P. So for that we have calculate this bracket part. So bracket part is 1 so we simply put another bracket. Fifty into 100 plus 40 divided by 1.04 to 10 to the power 6. This value is 7.85 into 10 to the power minus 5. 7.85 into 10 to the power minus 5, 13.85. Then P is equal to 13.85 divided by 7.85 into 10 to the power minus 5. So this value will be 13.85 divided by 7.85 into 10 to the power minus 5. 176 into 10 to the power 3. Okay, so this is 176 into 10 to the power 3 Newton, or simply 176 kilonewton. So this is the answer for the second pattern. So once again, if you want to revise how we have solved this, so our question is simply that a rectangular section of the beam is given 100 by width is 100 and depth is 250 mm. The span is 8 meters and is prestressed by a straight cable carrying an effective prestressing force of 250 kN. Its intensity is 40 mm. The beam supports a live load. Intensity is given 1.2 kN per meter. So our first part is calculate the resultant stress distribution for the center of the span cross section, assuming the density of concrete as 24 kN per meter cube. So for that we have to first obtain resultant stress. We have to obtain the pre-stress, bending pre-stress, and bending stress due to the dead load, and bending stress due to the live load. So this formula we know for pre-stress P by A, bending stress P by ZT at top and P by ZB at the bottom. Bending stress due to the dead load, MQ by ZT at the top, MQ by ZB at the bottom. Bending stress due to live load, mg by ZT at the top, mg by ZB at the bottom. Now we have to just feed the data. P is 250 kN, 15 over 3, A is 170 to 50 mm, 50 into 10 to the power 10 square millimeter square. Now section modulus Z is equal to I by Y. For top ZT, I by YT, I is BDQ by 12 from the CG of this rectangular section. BDQ by 12 we know. YT is D by 2 top from the neutral axis, D by 2. So BD is square by 6. Same ZB, I by YB, so BDQ by 12 and ZYB bottom from the neutral axis, T by 2. This BD square by 6, same value. We have just feed the data and obtain the result 1.0 millimeter cube. Now MQ and MG. So Q is the dead load intensity. So concrete density is 24 into 10 to the power 3 because 24 kilonewton. So 24 into 10 to the power 3 into 1000 cube into 100 into 50. So this value is 0.6. G is lab load density 1.2 kilonewton meter or 1.2 Newton per millimeter. We added both, result 1.8. So mq plus mg is simply 1.8 into WL square divided by 8. L is 8 meters, so 8000. So this value is 1.4 into 7. So now bending pre-stress is P by Z. P is 250 10 per 3 kilonewton into 40 millimeter, 1.04 into 10 per 6. This value is obtained we have here. Okay, so this value put 9.6. This bending pre-stress. Now bending stress M by Z 1.44 M into 10 power 7 you obtained here. Now Z is 1.04 into 10 power 6, so the value is 13.85 into 13.85 Newton per millimeter square. Now direct pre-stress P by A 250 into 10 power 3 100 into 50, this value is 10. So simply we at the top of the beam 10 minus 9.6 plus 13.85 is 14.25. At the bottom of the beam 10 plus 9.6 minus 13.85 to 5.75. Okay. Second part of the question is different. We obtain the magnitude of the pre-stressing force which balance the stress due to dead load and live load. So the resultant stress is P by A at the bottom or soffit of the beam, P by A plus P by ZB minus M by ZB. Okay, so this part of the pre-stressing force has to balance the stress, bending stress due to the dead load and live load, M by ZB. Okay, so we have equalized both, and for P is the variable and the rest values are feed, and we have obtained the P here 176 kilonewton. So thank you. This question has been solved, and other questions we solve in the next video. Okay, thank you.